okay?
Yeah, we're on.
All right.
Okay.
So people always filter in late because it's like so early in the morning. But
I know.
I always just start on time anyway because
Yeah.
I figure it'd help them.
Okay, so guys, I won't be using the room microphone and speaker, so if you cannot hear me in the back, you'll have to come up here to the front, right? Sorry about that, because it's just that wearing 3 microphones is kind of awkward, so I figured 2 are probably good enough and 3 would be silly, and yeah. Okay, so I don't know, do you want to do the honors?
I'll just
or
do
what?
like a quick introduction.
Okay.
Maybe. So Alex doesn't really need an introduction. I mean, he's a professor here at CMU. So if you paid attention to the co-authors of the papers we've been discussing, so Alex sort of keeps coming up over and over again. How many people here have read the Sherlock Holmes stories? A few, right? Like there's the Moriarty. Moriarty is like the Napoleon of crime. Sherlock Holmes says you can see his fingers, you know, sort of subtly influencing every crime in metropolitan London. So Alex is like basically the same thing, except for big data. Okay, so he's like the Napoleon of big data. So he was involved in a lot of the theoretical work and practical work on parallelizing stochastic gradient descent-like algorithms. He was involved in the alias SGD paper we talked about the other day. He's been involved in parameter server stuff. His algorithm, the parallel SGD, was the baseline we saw in Alex's talk on Tuesday. So he's basically all over the place, and he's going to give a talk about his recent work today.
Okay, so many thanks for the kind words and the introduction. So if you have any questions at any time, please raise your hands. So can you guys in the back hear me? If you do, please raise your hands. Okay, cool. That's good. So I have way more slides than what I can get through in the 80 minutes, so therefore there's no need to rush or push things, and the slides will actually be online afterwards. I mean, I can email them to William and he can put it up on his course website. Also, please do interrupt me at any time if something's not clear, right? Okay, so first of all, here's where you can get the code, right? Parameterserver.org. The latest dev release isn't out yet. This will have a greatly simplified but also slightly more limited interface, such that it's really ridiculously easy to take your single machine code and make it multi-machine capable. In other words, you just write really good single machine code and then you scale it up. There's a number of people who are contributors to the what was essentially published last year in OSDI. We actually have a contributor to the next generation in the room. So would the gentleman in the middle please stand up? So Chikong. So he's basically making everything happen to make our system very, very easily deployable in lightweight containers. So this is the next generation, and with that you should be able to run it in every cloud very easily. Well, the main credit really goes to the guy up on the left, so Mu Lee. So he wrote a large part. I don't want to mark him up. He wrote a large part of the code. Lizzo added cuckoo hashes. Dave Anderson is the systems faculty who keeps me from doing really stupid things. Junwoo does sketches. This team here is at Google, or at least mostly at Google. Vanya just escaped to Pinterest, so you should be able to see high scalability for, well, pinning pictures at some point. Well, okay, I guess if you want that. Yeah, so that's the Google team. I used to work with him until the end of last year. I am no longer with Google because it doesn't work with Google and startup at the same time. So, outline. So I'll talk a little bit about background models, hardware stuff. Some of this is going to be fairly familiar to you guys because you probably would have seen that machines do fail and just overall generally how you lay things out. But I just want to make sure that you understand the notation that I'll be using. The next thing that I'll then do is I'll talk a little bit about this bipartite design and why that's actually pretty good for what you need. as in, well, it's essentially a fancy version of MapReduce, if you will, with a lot of tricks added in terms of communication, and why you may not necessarily need to go way fancier than that. Then I'll go into a fair amount of detail on how to make all of this efficient, and this is probably going to be a bit of a departure from the other parameter server talk that you heard so far. And then how you can actually do clever things to improve layouts and so on if you actually have to deal with very large social networks. And in the end, I'll show you a few experiments. So that's the overall stuff. So everybody starts with a background. Computational advertising. So this, at some point, used to be, I don't know whether it still is, one of the most expensive ads you could actually bid for on Google. So basically, mesothelioma is the kind of horrible disease. It's lung cancer that you get if you inhaled asbestos mostly. And this is a wonderful opportunity for a lawyer to sue whoever might have given you this asbestos. And the lawyers are willing to pay easily $100 and more for an ad there. It's quite sad, but the point is I need to actually therefore estimate for a given query and a given ad what the chances are that the user will click on this ad, because my ad ranking is essentially based on the click probability times the amount of money that you're willing to offer. Okay. And you have a lot of that, namely about 4 million per minute. But that number has only gone up probably in the meantime, but basically there's a lot. Okay, apologies. iOS and OS X don't seem to be compatible in their versions of Keynote. So sorry about the layout, but basically here's what you do if you want to do simple click estimation. So you could, for instance, do logistic regression. The reason why you would do that as opposed to, let's say, support vector machines of margin classifiers is because you actually want to have click probabilities. And that's kind of hard to get with soft margin. So you have something like P of y given x is 1 over 1 plus e to the minus, y times f of x. Who has seen this equation before? Okay, all hands should go up because William surely taught you this. So then we take about the dumbest thing we could, namely a linear function class, w.x. You can do something way fancier than that. So for instance, you could plug in, well, a kernel method, you could plug in a deep network, but ultimately the logistic regression objective is kind of a decent choice. You might impose a sparsity prior. So this is basically if you think that not all attributes are really relevant to infer whether somebody's going to click on it. It also means that your ad serving infrastructure will have a much smaller memory footprint and you can serve faster. So basically sparsity is good for you because it actually saves you CPU cycles. And then in the end you have this mess, which is basically this optimization problem where you minimize basically how well the data is explained by your model. So you minimize over W, and then you have this penalty. Okay, this should be all super non-scary. So here's how you can, for instance, do this. So there's something called proximal algorithms, and they basically work as follows. You take a gradient update step, and then you sparsify. This is actually quite useful because this way your set of parameters will never really be dense, right? Because you always sparsify. You might get a dense gradient update, but then you basically knock out all the tiny terms that will make things sparse again, well, would prevent things from remaining sparse. And this is actually really, really useful if you, let's say, have 100 billion variables and you actually want to keep this all more or less in memory, because in this case, you actually want to make sure that your working set payload will never exceed it. And the good thing is that with the sparsity penalty, which is just a simple thresholding, let me show you a picture. All right, so this is basically what you do. If your coefficients are less than some epsilon, they are set to 0, otherwise they're just shrunk to 0. Well, actually I goofed up, and somebody should have picked it up because this is really how it goes, right? Okay, so guys, pay attention. Occasionally I insert errors, maybe deliberately, but mostly just by me being stupid, and then I need your help to pick this up. Okay, so that's exactly this function here. And so they decompose very nicely into coordinates, so you can do that quickly. Okay. So here's how the data flow overall works. So you have some parameters, and those parameters will be multiplied with the data. And I get some f of x out of it here. Then I go and compute the gradient. So this is basically just df of the loss. And then, once you have this, you take the gradient and you basically apply it back to the parameters. Right? This is, completely standard. You perform a right multiplication of the data with the parameters to get, the function values. Then you compute your gradient, and then you perform a left multiplication of your data matrix with that gradient to get, the overall gradient in terms of parameters, and that's it. So in other words, you have two operations. You have x times w, and you basically have x transposed g. Those are the two things you need to worry about, at least in a generalized linear model. Okay. Now, of course, if you have a lot of data, that's supremely awkward. So what you do is you shard things. And you would go and shard the data into, subsets for one machine each, and you probably saw that in, for instance, MapReduce, right? MapReduce, you partition your data, you compute then your parameter times data, and you do each of those on each machine separately, and then for each of those loss gradients, you just, aggregate, and then you transmit it back. Or you actually aggregate it where the parameters sit. That's still sometimes quite awkward because maybe a gradient is really large. So what you really do is you also partition your parameters onto many servers, and each of those servers takes care of parts of it. So we have two types of partitionings. We shard the data over machines, and we shard the parameters over servers. Hence, parameter server, right? That's really the basic idea. And so we can keep on going around in circles, and Hadoop, for instance, would actually do an okay job for that. But we need a little bit more functionality, so that's why Hadoop isn't good enough, so we decided to build our own. So in a caricature, you have basically the clients talking to the server, asking the server what are the parameters, such that they can do something with it. The clients do some interesting jobs. They then send an update back to the server. The server gets this update, it applies it, and it broadcasts things back. And as you can immediately see, the poor server will get horribly swamped because it doesn't have enough network bandwidth, it doesn't have enough CPU. So what you do is you therefore partition the job of the server into many servers, and that's why you have, many servers here, many clients there. And they all talk to each other in a bipartite graph. This is also really nice because now if I have more machines, all I do is I just make this bipartite graph longer. And if at some point my servers get overloaded, I just throw more servers at it. If my clients are getting overloaded and the servers are doing okay, I throw more clients at it. So depending on your workload, you may have different numbers for servers and clients. So for instance, it could be that the clients actually will have to do a lot of computation, and the servers mostly are just used for parameter storage and they don't have to do very much. In this case, you're going to pick servers that have very high network bandwidth, a small number of them, and you will pick a large number of clients with maybe not so high network bandwidth. So if you wanted to use that on AWS, for instance, you could pick something like a C4, 8x large for the servers, and you would pick maybe something like a C4 dot 2x large or 4x large for the clients. Okay, who has heard of those terms before? C4 8x large. Okay, so those in the room who have not heard about those things yet, go and Google this thing, go and get yourself an AWS account, play with these things. It's really, really useful. And you may be able to get like $100 for the free tier, make sure you get some practice with AWS. It's not rocket science. It's actually very, very simple, but make sure you work with this. Yes?
Students in this course have used AWS for assignments in the past.
Okay.
Some of them do know it.
Okay. So that's good. So then why didn't all the hands go up? Okay, thanks. So the other thing is never use the regular instances, always use the spot instances. Right? Because you get 8 times as much computation out of it. Right? Okay. Of course, you'll have to deal with machines failing, but it's actually very good practice such that you write code that can deal with failures. Right? Okay, so by the way, now, of course, deep networks are all the rage, and you might think, well, how does this very boring logistic regression relate to a deep network? Well, here's, one of those very nice Byzantine architectures where you have things like convolutions and max pooling and whatever, and again, well, you get exactly the same communication pattern. So as a matter of fact, Google Brain pretty much uses the same structure, except that they have certain optimizations that are specific for deep networks. So each of those layers will still need to compute gradients. And so what you then do is you can actually go and aggregate those gradients, synchronize them possibly off the GPU. You pull the data off several GPUs, put it into the parameter server, which may very well be now running inside your machine, and then you send it back out. Or you have a more optimized infrastructure for single machines and you tie multiple machines together. Stay tuned on that. Probably within a month or so, there'll be a very nice software release. So then you don't have to worry about Torch and buying machines with multiple GPUs anymore. Okay, so this is coming. Now, another thing, topic models. Who's heard of topic models before? Cool. So topic models are this case where you basically try to, and they're actually a very nice stand-in for a family of problems where you go and annotate documents or basically annotate objects. Those objects therefore have a persistent state. This is the text that the document, that corresponds to the document. And they have some, local state, which is, for instance, the topics associated with each word, maybe the cluster ID associated with the document overall if I want to do clustering, or the LSTM state if I want to do annotation there. So in other words, there are a lot of cases where you basically have local state. This local state is only important insofar as it helps you deal with the document while you're processing it. After that, you can dump it back to disk, and it doesn't require any memory. Or for instance, in the recommender systems, that's the user state. Whenever I'm not looking at a particular user, I don't really need to have the user state around. I can actually just store it on disk. And then you have a global state, and the global state is essentially the language model that describes, for instance, that maybe topic number 42 is about machine learning and scale, and maybe topic number 45 is my ping pony. So now, what this basically means is you have a processing pattern, and I'm not going to explain topic models in detail here because it's not relevant for the purpose of understanding the parameter server, but basically you locally process the document, you generate some updates. These updates need to be synchronized against all the other machines, and the local state needs to be saved back to disk. So the good thing is you can basically take a high-end single machine implementation for a topic model then, and you parallelize it by essentially just synchronizing the global state. You need to do a little bit of extra work, but it's not very much. Okay. So what I hope I've convinced you of is that there is actually a very large class of models that have order 1 blocks of order n terms. So you might wonder, why is it order 1 blocks? It's actually very simple. Because usually each block corresponds to an engineer building something. And most companies have order 1 engineers. Okay, exception Google, Facebook, and whatever, they have order n engineers, but most places have a small number of engineers who can actually generate such additional data blocks. However, they will have a large number of users, and that needs to scale. So what that means is that I usually will not end up with an insanely complex model that is the most general graphical model you could imagine. So if you, for instance, recall from your graphical models class, the example of the sprinkler and the earthquake and the burglar and so on, that's the example of, well, making things very general. And if you want to use inference in those models, I strongly advise you to look at GraphLab because it's just gorgeous for that purpose. I think it's very hard to beat it on that specific case. However, I think that a lot of machine learning problems actually don't quite need this drastic extent of generality. The other issue is that a lot of features are there that don't fit into memory. So for instance, personalized click-through rates, large inventories, actions, well, user states. However, the local model typically fits into memory. Yes, you can break that. So you can, for instance, take a topic model and insanely increase the number of topics or increase the dictionary. And if you do that, then of course you can break something that was not engineered to do this. And you would have probably seen a couple of papers which basically showed how Yahoo LDA fails if you use it way beyond the design parameters that it was engineered for. So, moral of the story, you want to engineer the system to solve your problem, not to solve some problem that somebody else thinks is relevant, unless they have a good reason. But the key thing is that you want to decouple the issue of data processing, which is what happens locally in each client, from the issue of aggregation, which is basically what happens in the server. And as long as you do that, you're actually in pretty good shape. Okay. So I don't think you need to see those pictures anymore because you've probably seen them. If you haven't, do a Google search for Domo, data never sleeps. And, well, I just thought I'd put on the side a little bit where we scale at. So at some point we talked at Netflix and they said, well, we are sorry, we don't have problems that are large enough for what you need. Okay, this is a really important slide. So I stole it shamelessly from Jeff Dean. And basically, so it's actually a really good talk that you should at some point go through. It's basically from a Stanford class where he gave a guest lecture about essentially scaling. And without necessarily looking at the specific details there, this shows you a lot of things that can go wrong and will go wrong in a server center. So in other words, do not assume that the machines in your server center will stay up. There's actually a very simple reasoning that you can do. So I'm not going to use a lot of math, but let's just quickly do this. So let's assume I have a computer that will crash only every 3 years. It's a pretty good computer, right? Okay. So let's say 1,000 days. MTBF, mean time between failures. Okay, so the probability that it'll crash in a day is about, 1 over 1,000, right? So I'm playing fast and loose here, but this is really just to give you the idea. So now if I have 10 machines and I run them for a day, then the chances that this machine will crash are 1 minus the chances that the machine will not crash, which is 1 minus 1 over 1,000, raised to the power of 10. And yeah, that's a really small chance, so maybe it'll crash about 1% of all times. And that's fine. I can happily tolerate that. So if I have a small academic research cluster with 10 machines, there isn't really much you need to do in terms of fault tolerance, checkpointing, and so on. I mean, yeah, sure, you probably write things out to disk every couple of hours, but that's about all you need. Now let's go to 100 machines, and we have this. And that's approximately 1 minus, well, basically, okay, well, let's actually do the simple thing first. We take 1,000 machines, and there it's 1 to 1,000, right? And that's 1 over E. So, rest is homework. Okay, I can get away with it because I'm standing here in front. You guys can't. Okay, so point is, this is frequent, right? So, in other words, in most of the cases that you actually run something, the machine will fail. It's now more common that things will fail than they wouldn't. So don't bet on everything going well. And as I said, MTBF of 1,000 days is crazy good. So stuff will fail, and you need to actually engineer around it, and that's, in a way, what we did. Laptop. Okay, good. So now let's look at the communication part a little bit more. So here's the parameter server, and this is what we do. And at the end of the day, you need to perform two different types of operations. And one is basically you send keys, values, and a clock. And the other thing is you receive keys, values, and a clock. Okay. Who here in the room has used version control before? Okay. Who ever had an SVN or a Git conflict? Right. Okay. So here's what you need. Here's why you need clocks. Right. So what basically happens is that different machines can crash or go out of sync in different ways. Right. And so clock is basically the equivalent of the version number of your LaTeX or your C++ or your Java file. And so this way you can avoid the fact that, let's say, maybe Qigong is really good at writing code, and he writes a lot of code, and he commits a lot of stuff in there, and I come along and I'm using an old version of the same code base, and I'm performing a git push, and this would completely destroy his work. But since his version number and therefore the number in the repository has moved ahead, I cannot just go and destroy all of his precious work. Instead of that, Git will come back and say, hey, Alex, you need to update to move up to the latest version and then incorporate. And essentially, you need the equivalent of this when you perform communication between multiple machines. Now, I cannot go into detail about vector clocks, and I don't know whether William covered this. It's probably more of a systems class thing. You might want to read up on Paxos, and it's, well, not super always clear the first time you read it. But basically, that version numbering is really important if you want to deal with failed machines. Because this way, for instance, you can make sure that I don't incorporate the updates from a machine twice. Because what could happen is the machine sends the data. Before it gets the information back that everything was incorporated, it dies. It gets rebooted, it comes back, realizes, oh, I still need to do the work, and it sends the data again. Now, since the version number has already moved ahead, the parameter server therefore knows, well, okay, this machine has already sent it, and so I cannot send it again. So that's essentially the reason why you need versions. Okay. And yeah, put and get is really just like in any key value stores. The trick is now to how to make this really efficient. Okay. So the general template is that, well, you basically, the clients, have the local view of all the parameters that they need. Point-to-point communication is really infeasible. There was actually a version of LDA by Max Welling where they tried to do this, and you pretty much now have to remember what you told every one of the other machines, and that unfortunately scales quadratically with the amount of storage, with the number of machines that you talk to. So this is not good. But when you actually synchronize things with a parameter server, you need to address three issues. One is a reconciliation protocol. So in other words, what do I do if I get different updates from different machines? How do I all merge this? Do I need to get locks and whatever? I need to think about a synchronization schedule. So basically, do I do things episodically? Will I require full locks? Can I allow for some delays? And then I also need to worry about how do I actually spread the load of work between the workers and the clients? And how do I do fault tolerance and recovery? And so there were like 3 papers that covered a lot of this. And what you probably saw in the previous parameter server talk is a fairly good copy of this. Yeah, it's actually deployed in a couple of places. Okay, so here's the architecture, a little bit more detail. You basically have server nodes, you have a server manager, you have a resource manager that runs Paxos to make sure that everything is, nicely fault tolerant. You actually have groups of worker nodes, each of which may have their own task scheduler. Okay, and then you have data. So why would you want to have groups? Well, the thing is, you could, for instance, have one group actually training your next, advertising model, and one group serving the advertising model to the world. And so this way, both of them need access to the parameters, and at some point you just flick a switch and you say, well, this group now needs to read the new parameters, and you can keep on doing this fairly efficiently. So that's why you need groups and namespaces. Okay, now let's look at key layout and recovery. Let's skip over this one because we're a little bit late. So who has heard of a distributed hash table before? Okay. Who's used a peer-to-peer client at some point in his life? Right. Yeah, sure, we all did. Right. So BitTorrent or whatever. Now, how does BitTorrent actually know where things are? Well, it basically attaches, individual chunks of files to random locations across the network. And then what you need to do is you basically need to find, for instance, the nearest machine that has that chunk. There's a lot of really nice work in a paper called Pastry by a guy called Druschel. You should probably read this paper at some point. It's very, very nice and prettily written and explains stuff really well. Okay, it talks about pastry routing and all that. Now, what we do is we actually just steal the basic idea of that, namely how to lay things out. So we go and basically the challenge that we need to address is how do we know and how do we determine which server has which key? So for instance, if I have a large advertising model, I need to know, which machine will contain the word Viagra and which one will contain the word mesothelioma and which machine does machine learning, right? So I compute a hash for each of those keys. And they are now inserted into a ring. All I do is I just wrap around the key space by, pasting together the 0 and the n-1 part. And so this way I get a more or less uniform layout of keys over that ring. And then I go and randomly partition this ring over servers. So I do this by hashing the servers also into the same ring. And I simply say that the server takes care of the segment to the right of this ring. So for instance, server 3 will take care of this, server 1 would take care of that part, and so on. Now, what you see here is actually several arcs emanating from a server. What happens here is that I'm basically inserting each server more than once. The reason for doing this is that if I were to insert a server only once, I could get a situation where some servers have very little to do and some servers have a lot to do. So by inserting, if I have k servers, if I insert each server log k times, I can make sure that with high probability, none of the servers really manages to slack off and none of the servers get seriously overloaded. It also has a couple of other really, really nice properties that I'll get to in a moment, but this is just standard load balancing. The good thing is that if I have my hash function, this is all I need to know where all the keys and all the servers are. So if I give you a list of all the servers, you can immediately figure out which server has which key. Because, well, for this key, which sits here, all I have to do is I just have to know where all my servers sit. Well, I know that one sits here, one sits there. And so I know that I have to ask this server for the key. Right? Because there's a very simple unique mapping, so I don't really need to have any master table that determines how things are being laid out. So think of this like as if I had a file system where I don't really need a directory. So as long as I know the file name, I will know where the file sits. Which is kind of cool, right? Now, of course, you could worry, well, will not two keys map into the same location? Well, yes, that could happen, but one way, for instance, to fix this is just to have longer keys. There are fancier ways to fix it, but basically, if you have keys that are twice as long as what you would need for the exact mapping, you're safe. This is birthday paradox 101. Now, the nice thing is that in this ring, I can also then easily determine who is the fallback server for a given key. Because what I simply do is it's just the next one in line. So I'm lining up all my servers, or virtual servers, and I basically say, well, if you don't take care of it, the next one will. And if that one doesn't take care of it, the next one will, yet again. So let's flatten this out. So here's what happens. So I have, let's say, 6 servers here, and this would continue, and I have, well, in this case, 5 sets of keys. And server 1 needs to take care of segment A. And then if he doesn't take care of it, then, well, basically server 2 or server 3 would also be able to take care of it. Right? So this is fairly straightforward. Likewise, for the red guys, well, this machine would take care of it, or that, or that. Right? And then for, this is basically server 3, server 4, server 5. So what I try to do is to make sure that those replicas are as fresh as possible. Because what I want to make sure is that if I have an ad serving solution and the machine dies, well, that I can keep on serving ads. So I cannot actually afford having to reboot and bring up a new machine and do the job, because actually getting the data into the machine and all that may be too costly. So I want to be able to have a hot failover, at least if I lose only a small number of machines. Okay, so let's assume, well, disaster strikes and server 3 dies. Okay, so what do we do then? Well, actually for segments A and B, nothing happens. For segments D and E, also nothing happens. So they're all okay. Except that we now need to repair this, because we need to make another copy, because we lost this copy here, and that copy there. So all you do is you just copy. That's a very simple operation, and it's easy for me to find out that the machine that's in my chain has died. Okay, so I need to just move one step further in the chain. Now the next thing that I need to do is I need to make sure that the keys in C will get served again. So that's also very easy, because the data already sits in server 4 and 5, right? So all I need to do is just now say, well, server 4, your segment is now larger, so there's no data copy that occurs. It's just a logical operation, and then everything is good. Okay, so this is also easy. And then I just have to do a little bit of a repair. Which is basically I just make a partial copy. So what you saw is that having a machine fail is a very, very simple thing, and I can do this without really causing a lot of disaster. The nice thing is also that this means that I can dynamically drain machines out of my pool, because this is the same thing as just failing them over. Well, okay, if I know that I'm going to kill them, I can do a couple of things easily, but it basically means that your code for machine failure and for shutting them down is very similar. Okay. Now recovery is a little bit more tricky. The issue is that, well, how do we all of a sudden switch things over on the fly? Because these servers keep on getting updates. Okay. So for the replicas, it's trivial. I just, copy the replica over. So this one is easy. This one's easy. Now for this one, so when server 3 comes back, this is the critical part. What happens is I basically need to address the fact that I keep on getting lots and lots and lots more updates while I'm trying to tell a new server what it's supposed to do. And so if you have a 1 gigabit network link, and I'm copying state out at 1 gigabit rate, and I keep on getting updates at 1 gigabit, I can't win, right? This is really, really hard to win this. So this is another part where the virtual servers come in handy. Because I can devote all my outbound bandwidth to do the pre-copying. And the inbound bandwidth is, 1 over a number of virtual servers. So it's 1 over k. So I have a smaller segment, it's size 1 over k, and I only get a stream of 1 over k data incoming, so 1 over k times 1 over k makes the cost penalty 1 over k squared. So therefore, it's a really good idea to have more than one virtual server also to minimize that delay. So in hindsight, it's utterly obvious. I spent more than a week on trying to figure out on how to do this. The hindsight is really, really simple. And yeah, probably a whole bunch of systems people before me did this, and they probably just smile about it. Yeah. Anyway, this is a very simple trick that actually helps a lot. So then now you need to worry about communication. By the way, are there any questions so far? Because I've gone through a lot of stuff. A lot of it is more systemsy than machine learning, really. So some of that may be kind of scary for you. Any questions? Everything clear? Wow, okay. You guys are very smart. So basically, what we need to do is, when you send data, you want to make sure you're really nice to your network, because the network's kind of the weakest link, and we need to be able to, figure out what happens here. So first of all, you don't want to send singletons. That's the easiest way to destroy network performance. Yes, we did that in the past, and that's really bad. The second thing is, don't write your own communications library. Use one that somebody else has written, because that means you don't need to maintain it. So protocol buffers and 0MQ are pretty good. And that'll just take care of it. Yeah. What you can do is you can basically block things together. So this way you don't get packet overhead. And you could, for instance, decide, well, you will finish one small iteration or a mini batch. And then, well, you make sure that you don't get too much out of sync, and I'll talk about this in a moment. Okay. So the other thing that you may want to do is, when you send a message to one of the servers, that server at some point will come back and say, yeah, I got it. This is important in terms of the vector clocks as well. Now, if it goes and then sends the replica, copies out to the replicas, and then comes back, this will take some time, and it also uses a lot of bandwidth. So what's actually quite smart is, if you have several updates for a particular key-value pair, that you pre-aggregate them on the server, it then only sends the aggregate copy out to the next machines, and then the ACK comes back. So that adds a little bit of delay, but it actually saves a lot of bandwidth. So basically, the owner of the key-value pairs on the server part of the parameter server acts as an aggregator before sending things further. I mean, it's kind of straightforward, but it's quite important to think about it. The other thing is, a client will only really send the keys that it cares about. Likewise, the server will only request from the client or send back to the client the keys that we care. So here's a simple example. So here are all the keys, right? I have 6 keys. And server 0 has the first 3, server 1 has the second 3 sets of keys. Now, client 0 needs these keys, right? And so what it would actually do is, it would really only request these keys from server 0 and these keys from server 1, and would not request those. And likewise, client 1 would also only request what it needs. So that already tells you that, wouldn't it be nice if we had a nice way of laying out data and, well, key requirements, such that each client only needs to talk to a small number of server, and also that it only needs a small number of keys. This is actually a submodular load balancing problem. I'll quickly get into this towards the end of the talk. And you can actually optimize for that and save quite a bit of bandwidth. So this is easy. Now, what I haven't talked about yet is how to actually make all of this efficient. So what you can do is you can actually go and design an amazingly clever scheduler. And that amazingly clever scheduler would take care of things. But the problem is, if you do this, well, okay, so basically the problem was we didn't have anybody on our team who really understood schedulers very well. So we decided to do something that is just as easy. You basically tell people when to shut up. Right? So you basically want to make sure that you only send data when it's necessary. You also want to make sure that, for instance, when you send key-value pairs and I send the same key-value pair list the next time, that I don't send the keys along again, because the other party already knows what the keys will be, so I can cache this. It's much faster to cache it locally rather than receive it again. And it also means that when, for instance, I'm already almost converged on some parameters, I will not send them. And so I'll walk you through the details. So the first thing is you just compress before you send things over the wire. And Zippy is pretty good. Google Protocol buffers will also do a good job at compressing things. So don't try writing your own serialization library, because almost certainly yours will be worse than what Google Protocol buffers does. I mean, this is written by Jeff Dean, and he's good. So don't compete with Jeff Dean. Okay. The second thing is you can actually go and do things like quantization. So, for instance, in some optimization algorithms, you might want to send a gradient and also some information about the preconditioner. So this is basically like a diagonal rescaling, right? So AdaGrad, for instance, would have stuff like this. So the point is, quite often you don't actually need very high precision. You just need sort of the information that whether you should increase or decrease that parameter. So you could go from double to float. You should do that anyway. That'll just double your memory bandwidth. It's not just that you will need less memory. It'll also take you less time to get that data into your processor. So try to get away with float whenever you can. The next thing is, you could say, well, why should we stop at float? Did Dee Scully give a talk here in the past? Okay, so he already told you all about randomized rounding. Cool. So yes, we can do that too. We can basically quantize further. And here's a simple way how to quantize. So let's say I have a randomized rounded gradient, GR, which is basically the gradient minus, some reference threshold. So I could, for instance, use this as, maybe what I would expect it to be. And I, just go and divide by epsilon, which is my precision. And I just take, floor plus a random variable. And this one is just, randomized rounding. It's just basically, I just take the difference between this and the next quantization step, and I round. Now, why is this a good idea? Well, for a single client, this is maybe not so great. But if I have 1,000 clients, just by having the data from 1,000 clients means I actually get pretty much what I would have expected to get back anyway, because I'm averaging over 1,000 randomized rounding results. So this way, I don't actually pay very much penalty anymore. So, 8-bit is quite often good enough. So what we did is we went from 16 bytes to maybe about 2 bytes. Okay, so what happened is basically you made your network about 8 times faster. You also made your network twice faster by not sending the keys. So now we are basically saving a factor of 16, which is like going from a gigabit network that you can buy for $20 to a 10 gigabit network that at the moment you have to ask your professor whether he will buy your machine for it, right? So by being smart, you can actually make up for crummy hardware. Okay. The next thing that you can do is thorough sampling, and this completely got messed up in the layout. So first of all, you should look for Duffield, Lund, and Thorup sampling. And let me describe the algorithm to you because it's so amazingly simple. So you go, and, basically the goal is I want to turn a possibly dense vector into sparse vector. And I want to do so by keeping maybe only the, top k terms around. The problem is if I only keep the k largest terms around, I will actually incur a reasonably large error for all the smaller terms, right? So if I just, throw everything away that's smaller than the threshold, that may not always be a good idea. So what you need is something that will give you randomized rounding and sparsity and, give you only maybe k terms. So this is very easy, at least in hindsight. And the algorithm, let me see whether I can fix this mess because it's really terrible. Oh man. Okay, that should do. Yay. Here we go. So what you do is you basically take the magnitude of the gradient and you divide it by a random number. That random number is drawn from a unit interval between 0 and 1. And you get some score Qi out of it. And now what you do is you pick the largest k terms based on this score. So this is a priority. This is why it's called priority sampling. And then you basically give them a weight, which is either GI, which is its own weight, or you pick the k plus first priority, right? So it's basically gk plus 1 over alpha k plus 1. This sounds utterly counterintuitive. Why on earth would something like this actually do something useful, right? So here's why it does. Let's first look at the picture and then look at the proof, because the proof is super simple once you think about it. So first of all, on the left hand, you see what happens. So you have some original weight. You go and divide it by, those random variables alpha, and you get some priority out of it. Right? And now, whenever and let's say, well, we pick only the top 3 guys, right? So now we know what my threshold is for the 4th one. And now what I'm doing is, whenever the score is higher than this, I use that score. Otherwise, I will use this as my priority. Okay. So here's why it works. So let's assume I have a single term that I haven't added yet. So basically, I have a single, GI that hasn't been added yet, and I go and pick, the kth largest priority. Okay. So then what I need to do is I need to check whether that gradient GI is in the set and also what its weight will be. Because without loss of generality, if I prove this, then I've proven that it works for everything, because the order doesn't really matter. Okay. So now the thing is, if my and so basically this is my threshold, and this is an arbitrary threshold because we don't really control for that. This is basically tau. So now, since I'm dividing by a number that's less equal than 1, if GI is larger than tau, it's automatically in the set. That's by default. If it's not in the set, then, since I'm dividing by that number, it's really the ratio between GI and tau that determines whether it's in the set. Okay. So therefore, it's the min between this and that. And so now this really wacky weighting is really just weighting by the inverse probability here. That's this thing here. Yes?
What's the actual statement that you just proved?
Okay, what I just proved is that in expectation, that the expected value of each coordinate is exactly the true coordinate. That's what I proved. So this is the simple part of that paper. The paper then goes on and shows that essentially this sparsification is optimal relative to a k-sparse variance reducing rounding. So basically, there is nothing better that you could do. And it gives you this very simple algorithm. I mean, it's beautiful, right? But this is the simple part of the proof. Enjoy the rest if you have time. So by all means do. And yeah, so this is a sparsifier. Now, the reason why I went through this is because you can use the sparsifier to sparsify your gradients. So if you might have, 10 million gradient coefficients that you want to send, but you really want to send only 100,000, you use the Storup sampler. Right? And so it sparsifies. You could also, like an active set method, decide to send only the terms that are, well, basically, violating constraints. So there's a lot of things you could do there. And it does help. Now, I do believe that we can still improve this. So what you're seeing here is, as we run the algorithm, we get about a 20-fold benefit over just sending all the gradients. A lot of this up here, I think, is we could get rid of simply by the fact that initially you don't really need to have a particularly good gradient to know where you're going. But basically, the good thing is all of those filters are composable, right? So you can use the thorough sparsifier combined with the discretization, combined with deciding, well, okay, if my constraints are not active, I don't have to worry about them anyway. And so the composition of those filters will, for some algorithms, obviously not for all of them, give you considerable network bandwidth savings. So that's the idea of how you can actually squeeze a lot more bandwidth out of a lame network. Of course, if you're working on Susitna, that's not your problem. Who's ever ran jobs on Susitna? Okay, one person. Okay, so then basically it's this Opteron system with very good GPUs, an amazingly good network, and, well, quite mediocre CPUs. So in this case, well, network savings isn't your biggest goal. So, well, the reason why I'm mentioning this is because when you actually apply those optimizations, make sure you're optimizing for the constraints that you have in your system, right? Because by applying those filters, the algorithm will maybe take 1 or 2 more iterations to converge. You are going to spend more computation on it. Now, if you have a system that is essentially CPU starved and really rich in network bandwidth, that's the worst thing you could do. So in this case, just blast everything over the network and make sure those poor Opterons don't suffer too badly, right? On the other hand, if you have something with a really crummy network and very fast CPUs, yes, be smart about what you're sending. So this way, yes, of course, you can basically wreck any algorithm and show that it doesn't work by just, picking the wrong design parameters. But no good engineer would do that. Okay. Clocks and consistency. So let's go through that a little bit. Because you may have heard some arguments about why bounded delay is good or why synchronous is good, or why fully asynchronous is good. And it's true that there are some algorithms for which you need one or the other. So for instance, the really cool Hogwild paper, coolest thing in it being probably the name, is that fully asynchronous actually works quite well. But then there are some which need some bounded delay, and some very brittle off-the-shelf algorithms where you really haven't thought very much about it, they may actually need full synchrony. So the question is, can you deal with that? Well, and people have fought battles about which side you should pick, and it's actually a stupid battle, because you can just have it all, right? So if you think about it, here are different ways of encoding consistency. So sequential consistency, I've just written it as this dependency graph, is basically, where you need 0 in order to do 1, in order to do 2, and so on and so on. Eventual consistency just means, well, as long as at some point I get all the results, it's good, and there's no real dependency. Bounded delay would mean that, okay, I'm willing to tolerate some delay, and the point is, computers are good at traversing graphs and at dealing with that dependency graph. If you ever installed Linux packages, you know that, right? It's like you want to install Emacs and all of a sudden it asks you, would you like to install those 100 packages, right? Basically what it's doing is it's actually working through a dependency graph like this one and working it through until all the requirements are satisfied, right? And then at some point you can get into dependency hell when you're upgrading, right? So the point is, we generate those graphs and we just process them with a task processing engine. So if you change your algorithm, you design a different graph, and off you go. And the good thing is, you can do all of this on the fly, so you can decide, well, okay, I start off with maybe, eventual consistency, and in the end, I really want to make sure I get the updates from everybody. Well, I can do that. So I can change my models by just dynamically updating my graphs. And it also allows me to move jobs between, processing units. There's a really cool package called Minerva, which does that for deep networks, except that they have way too fine granularity. Again, stay tuned. This will get fixed. Last thing is, well, we need version numbers, right? Now, if you have a version number, if you will, for every single key value pair. So key value pair is basically, let's say, a floating point number and then the name of that, right? And you need to basically store when the last time was you saw an update from any given machine. So if I have 1,000 clients, that means I need to store 1,000 numbers for every key value pair. So 1,000 numbers for every 16 bytes is awful, right? You don't do that. So now think of your file system, right? You basically have access information about when any byte on your disk was created, sort of, kind of. And still, you don't actually pay a lot of overhead. That's the case because you have essentially version numbers or access times for an entire file at a time. So as long as you can keep large blocks with a version number, that's fine. So you don't pay much overhead. And if I have maybe 1 million keys and I have 1,000 version numbers for them, I don't care. Now, of course, sometimes you will get partial updates, and then you just need to split your range. And that takes care of all the versioning. And so you don't have to hack things like Dynamo. So by the way, this is a cool paper that you should read by DeCandia et al. So look for Amazon Dynamo and DeCandia. So if you're using S3 or similar things, you're probably using that technology underneath. Okay. But they had to hack it because they didn't have the luxury of having larger segments. So they actually said, well, okay, let's just keep, let's truncate our vector clocks to a recent history of, 10, 20 clocks. And then, of course, if you get, partitionings and mergers, horrible things can happen. Here's an example of what happens there. And how much time do I actually have left?
15 minutes.
15 minutes. Okay. Okay, good. Okay, so now what I want to show you is also a few cool new things about the layout. So what I first told you is, just, partition your data and everything's good. Right. But actually, if you think about it, let's say I want to do spam filtering or anything else, and I'm a big company and I have data from different countries, right? Then it's probably a good idea if I put all the English documents into one set of machines and the French ones into one and maybe the Chinese ones into one and so on and so on. So in other words, it makes a lot of sense to actually partition by content. Does somebody know what is going on behind there? It sounds like a gigantic fan. So basically, what you want to do is you want to make sure that you actually have each machine only process a small, coherent subset of the data, such that this machine, more or less, if you will, can become an expert in that data as opposed to having to store all the parameters, synchronize everything, do all the updates for everything, right? And that actually turns out to be some modular load balancing. So in other words, can we move beyond this random key layout? And so there's a little bit of disagreement that I have with the GraphLab team because they pretty much argue, well, you can't really win very much, and we believe you can actually win a lot. So let's have a look at what happens. So because there are actually two things that I need to worry about. First of all, I need to worry about, if you will, which machine gets which documents. Secondly, you need to worry about which server caches which keys. And for convenience, what I'm often going to do is I'm going to co-locate one server and one client. That has the advantage that if I'm really memory starved and if I do something like network factorization on very large social networks, this will actually happen. That this way I just halve my memory footprint. So it's really something you want to do. So let's look at a simple case where I have documents, x1, 2, 3, 4, and they have certain values for certain keys, right? These would be basically, for instance, your bag of words. So then, well, x1 only needs word 1, x2 needs only word 2, x3 needs words 2 and 3, and x4 only needs word 2, right? So you basically have this bipartite dependence. So what I want to do is I want to go and group things in such a way that, quite preferably they don't have a lot of network traffic. Because if I need to request, my key from another machine, well, of course, I need to hit the network. So if you have graphical models, you get a similar thing. So it's not a bipartite graph here, but what you can basically do is you go and build a clique graph. And so now the clients are the vertices and the servers are the cliques. Right? And again, you want to make sure that, within a clique you have all the parameters together such that you can do something interesting. The standard graphical models. Okay. So it's a couple of goals. So first and foremost, you must not run out of memory, because nobody will buy you extra memory. Right? So therefore, I can possibly ask for more machines, but I probably cannot ask for memory upgrade in the machines. Okay. Of course, I want to be able to get away with as small a number of machines as possible, but you want to make sure that that you minimize the maximum memory footprint for any given machine. Right. So it's the worst machine, the one that uses the most memory, that's the one that you want to avoid. You should preferably balance the workload over clients. That would be really nice. And you really should minimize the communication cost. So, in other words, in terms of priorities, this is priority number 1. This is priority number 2. This is a nice to have. Because network and memory are really the hard constraints. And so without loss of generality, I'm just assuming that we have bipartite graphs, because for the other ones, I just showed you what happens. Okay. So here's the optimization problem. Basically, so I have vertices U and V, and the U's are the ones that I want to partition here. Now, what I basically need to do is, for any vertex U, I need to have all the V's, which are, the bipartite neighbors, around. Okay. So, therefore, what I want to do is I want to make sure that the maximum of the number of neighbors for any vertex group U is minimized. Right. So that's exactly this bipartite graph. So, for instance, if I was to pick x3 and x4 in one group, then I can first of all see that by adding x4 to x3, the set of my neighbors doesn't actually increase. And the set of neighbors here, of course, is this thing here. Now, the set of neighbors for this machine here is just that. And the set of neighbors for this machine here is just that. So if I have, therefore, a grouping which is basically U1, U2, and U3, then the maximum cost is 3, because it's exactly that yellow group. And that's what you want to minimize. Now, who has heard of submodularity before? Okay. Well, not so many. Okay, so let me quickly give you the idea of submodularity, because it's a really useful concept, and there's a lot of really cool algorithms that you want to deal with. Okay, so when you were little and you got $1 or whatever other currency, you were probably happy, right? That made you quite much happier, because maybe you had $10 or maybe $100, so getting an extra dollar was a substantial thing. Now you're all on student scholarships, and if I give you $1, then, well, sure, it's kind of nice, but yeah, so what? And if, let's say, at some point, our Dean Andrew Moore comes to William and me and says, hey, Alex, you should be happy you're getting $1 pay rise, we will probably not smile. Because we'll probably think, what on earth is going on here? So what you saw here is this diminishing returns property. That dollar is the same worth, for in absolute terms, but the more you have, the less the incremental gains from it. Okay. Now, this is for a simple scalar case. You can define the same thing for sets. So, for instance, in our case, this is set cover. So basically, for every vertex in the set U, I can ask, how many extra vertices in the set V will I have as neighbors? And that number can only decrease with the number of other elements that were already in the set U. Right? So for instance, here, if set U3 is empty and I add x3, this will increase the number from 0 to 2. If x4 was already in the set, then this would only increase the number from 1 to 2. So basically, the increment is decreasing given the set that you have so far. There's a lot of cases where this happens. And the good thing is that the greedy algorithm in these cases is usually very good. So submodular greedy optimization is a really good strategy, and you can actually get nice optimality guarantees and all that. So that's kind of nice. We have a submodular load balancing problem for which optimality guarantees are a little bit harder. There are some randomized algorithms which will give you this, and they scale with, the 6th power in the size of the sets. And if you have, 1 billion documents, then the 6th power in the size of the sets is the non-starter. So basically, how do you make it cheap? So you go and read the paper, and you basically try to get rid of all the powers in the algorithm. And yes, okay, the theorem suffers, but the algorithm still works very well, which is exactly what we did. So the paper that we looked at is one by Switkin and Fleischer, and it takes care of that. Okay. So essentially, here's how it works. You pick the currently worst client, as in, the one that has the least to do. You pick a random subset of candidates in U, and you basically optimize a submodular minimization problem. And this is really expensive because, well, first of all, it's a randomization. You don't actually get the best guy, and then you have to solve an optimization problem. So what you do is, instead, you basically greedily just add one vertex at a time. So this does sort of approximate load balancing in terms of work, but you're basically filling up the one machine or the one set that doesn't have too many neighbors yet. And the good thing is you can actually implement that in its own right on the parameter server. So the parameter server first runs a pre-processing step to figure out how to balance the real data, and then it does with the real data whatever you want it to do. And then the other thing is, now that we know what the partitions in U are, we need to figure out what the sets V are. That turns out to be actually an integer programming problem. And usually integer programming problems are intimidating, right? The good thing is that there are a whole bunch of them which have constraints in such a way that all the vertices of your constraints are integers. This is called total unimodularity. And whenever you have total unimodularity, you should remember this word. Let me write it out because it's a lifesaver. Whenever you have that, and they're fairly simple to check conditions, it tells you you can ignore the fact that this was an integer programming problem. You can relax it into a linear program, and the world is nice to you. And you can find integral solutions. Or more to the point, one of the vertices will be in the solution set. Okay. So, important statement. It doesn't mean that if you run the program that you will get an integral solution, but then you're on the facet, and if you walk around on that facet, you will find a vertex that's just as good. So this is a really useful tool for turning combinatorial problems into linear programs. We got lucky in this case. So that constraint problem actually was totally unimodular. And we found out by first implementing the algorithm and then squinting it and thinking, this is actually a nice problem. By the way, can we prove optimality? And yes, we can. And so what you do is basically you just greedily, so it's very simple, you just greedily go over all the vertices and reassign them to minimize network traffic. And 2 or 3 passes will do, and you will get the optimal solution. Okay, so I'm not going to go into a lot of detail here about the integer program because I don't think there's enough time. I want to show you maybe a few pictures, and basically that's the difference that you get. So this is for, as we increase the amount of data, the random partitioning will actually require a lot of network traffic, whereas if you're smart about how you lay things out, you can save massively on the network. So this is important, especially if you have to deal with things like Justin Bieber, right? So if you ever wanted to crawl Twitter, not that I would recommend it, you will probably a good idea is to start with Justin Bieber. Because he's the single highest degree vertex. I think about 3% of all Twitter users are connected to him. On top of that, he has about, my guess is probably now over 100,000 people who he follows as his closest friends. So he must have a massive media staff. Bottom line being, this is a really good place to start. Unfortunately, this also means that any inference algorithm that you do on the Twitter graph will very quickly end up with Justin Bieber being the variable across which you need to propagate a lot of messages. So that's exactly why you need to worry about him. So I heard that actually at Twitter, and I don't know whether it's still true, they actually have a couple of machines just dedicated to processing just what he does. Okay, so this is not just a made-up problem. You want to care about it. Yes, okay, you get good speed-ups. And yeah, our partitioner works better than other partitioners before us, which is not very surprising because, well, basically what we did is, it's the first algorithm to specifically target the objective that you care about for this problem partitioning. So usually when people talk to you about graph partitioning, they will try to partition the graph into meaningful segments, right? So in other words, you talk about social graphs and maybe you find, this group and that group and that group. And that's really nice if they're sort of from comparable size and you have exactly the same number of machines as you have meaningful groups. But if you have 100 machines and you get all of Twitter, you have no reason to believe that Twitter exactly partitions into 100 groups, right? So what you actually care about is communication efficient and otherwise fairly meaningless partitions, right? And that's one of the reasons why you can actually do, why by engineering something specifically for that, you can get massive savings. So the morale here is, don't be scared of math. Make the algorithm simpler until they actually run in linear time as you want it. And make the right approximations. Okay, so I will conclude with a couple of experiments. So for logistic regression, first of all, it means you can actually write very simple code. So 300 lines of code will give you the parameter server logistic regression. Well, okay, we kind of cheated here in the sense that, of course, it's probably by now over 10,000 lines of code, around it. But at least the applications code itself that deals with logistic regression rather than the parameter serving is fairly compact. So this is essentially good software engineering to factor out things that you can reuse later for other purposes, such that the code that you as a machine learner have to write is small. Because most machine learners are maybe only okay systems engineers. And there are other people who do that way better. So let's use them. Then, well, yes, there's a convergence theorem, but the fun thing is more this. So this is for a fairly large system at a fairly large company that is not Google. But it's basically about 1,000 machines, so that's about 16,000 cores, half a petabyte of data, about 100 billion variables, 100 billion observations. And what you can see is that, well, the green curve and the red curve are more or less the same, right? They're just shifted relative to each other, which isn't very surprising because they pretty much run the same algorithm. But the green one is without the parameter server. The red one is with a parameter server. Do you have a question? Or? Okay. The blue curve is an inferior algorithm, and you would expect it to work worse, and it does worse. Okay. But the other thing is basically within an hour, on 1,000 machines, half a petabyte is done. And you still do care about the differences here because that's money. The reason why it's actually faster is because, well, essentially, the parameter server spends a lot less time waiting and a lot more time computing. And that's mostly due to the bounded delay. So you can actually see that System B is a little bit better on the computation side, because it needs one iteration less. However, since it spends all the time waiting, it takes a bit longer until you're done. And you can use it as a stream processor. So if you think about it, you can basically just feed the data through and aggregate. So have you guys heard of the count min sketch? Yes. Awesome. Because this is exactly what we're doing here. We're basically trying to scale up the count min sketch to deal with very large numbers of inserts at the same time in a distributed fault tolerant manner. Right? Because otherwise, that poor machine that takes care of the count min sketch, once it runs out of network bandwidth, your game's over. So what you want to do is you basically want to have a lot of machines taking care of the count min sketch, and then the clients are now just machines that insert or query the server. So the good thing is that with very little modification, we could just go and take the same piece of code and use it for a distributed count min sketch. And yeah, you can do clever things beyond that. Okay, so here's what you get. You get basically over 1 billion inserts per second on, about 15 machines. So that is a decent insertion rate. So for calibration, here's why I wanted us to get to 1 billion. Because this is about the number of internet requests that you would get at per second worldwide. So you could basically sketch all of them in 15 machines. And yes, we can fail over and, time to fail over and repair is under a second. Okay. Yes, you can do deep networks as well. So this is basically on EC2. There'll be a lot more coming out on this. Stay tuned. So you get good speed up. And you can, I guess I'm pretty much out of time here, and people are already walking out. So I'll skip the topic models, except that, yes, you can do this. Okay. You've seen all of that at some point. Yeah, that's 60,000 cores. A good friend of mine at Google told me, hey, Alex, there's this one cluster that's currently free. And so we just went for that. And after that, my manager told me, this was an expensive experiment, 6,000 machines. I hope it was good for something. And yeah, that thing actually, in the meantime, is making Google good money. And yeah, so just for calibration, and this is actually more of a warning sign. So this is the largest nuclear reactor in the United States. And so now the machine has about 10 cores. I think they probably ran at least 500 watts. So that's 3 megawatts. So in other words, that's 0.1% of a nuclear reactor that we're using up. Okay, so this needs fixing. So in other words, the next thing is to get it back from 6,000 machines to maybe 600 or maybe 100 machines. We're well on our way for that. Some tricks are, for instance, you switch the processing architecture. Some tricks are you basically start designing a lot less dumb samplers. And I could talk a lot about that at some point. But basically, this is actually not necessarily something to be proud of. But I think in what we're doing is we're going clearly in this direction here for performance. If you want to have convenience, use GraphLab. Right? And yeah, that's the entire team again. Yeah. Okay.
So we're a little over time, and after this. So I guess people want to grab Alex on his way out for questions or send an email. Otherwise, I'll talk